All right, our problem is a skateboard is perched at the top of a 5-meter long, 15-degree incline is shown. The skateboard is released from rest. How much time will it take to reach the bottom of the incline? And how fast will it be going when it gets there? Okay, so here's a picture of the problem. Let me zoom out a little bit. So, you know, what's given here is, you can call this delta x is equal to 5 meters. And, well, the angle of incline, theta, is obviously 15 degrees, as shown in the picture. Our starting velocity, v naught, is 0. Okay. And, all right, and so what we're trying to find is, well, how much time it takes and the final velocity when it reaches the bottom. So let's solve it. Well, in order to find the time and the velocity given the initial velocity and delta x, this is obviously a kinematics problem. And so what we're going to have to do is use force to figure out what the acceleration is. So if I draw a free body diagram of the skateboard, I'll just draw a little box with wheels on it like this. Here's my skateboard. I've got gravity pulling it straight down, mg. Now I didn't give you the mass, but as I said earlier, if I don't give you the mass, that probably means it's going to cancel out. Now we've got a normal force, right? Here's our solid surface, and it can push the skateboard perpendicular to it. The wheels eliminate any friction, so this surface cannot apply any force that's parallel, but it can apply a force to this that's perpendicular to that surface. We call that the normal force. Okay, and so and that's it. Those are the only two forces acting on it. There's no friction force. There's nobody pushing or pulling on it. Okay, it's just gravity trying to pull it straight down, but the incline pushing on it like this, and so that's it. So what we need to do now is say, well, we're going to make down the incline the x direction, perpendicular to the incline is the y direction, and then we will take this force and break them up into their x and y components. So you have this one, well, it's all in the y direction, the normal force, but the force of gravity now has x and y components. So there's the y component, and there's the x component. Now, we said before, if this is theta, the angle of incline is theta, then this gets rotated by the same angle theta, so theta is up here. So mg is now the hypotenuse of a right triangle. This is the adjacent leg. So to find the adjacent leg of a right triangle, you take the hypotenuse and multiply by the cosine of the angle. This is the side of my right triangle that is opposite of the angle. So it's the hypotenuse, mg, times the sine of the angle.
Teachers, please excuse the interruption. At this time, please release your student senators to the library lecture hall. Again, please release all student senators
Who's our student
to the library
senator?
lecture hall.
Yeah, you didn't go last time, right? Yeah, you better go. So let's sum the forces in the, you know, if you need to stay, you can stay, because we do have a final coming up. Sum of the forces in the y direction equals ma in the y direction. And I don't know why I chose the y direction to do first, but I did. So all that does is say, well, there is no acceleration in the y direction. So I've got this normal force in the positive y direction, and I've got mg cosine theta in the negative y direction, and the skateboard is not going to accelerate at all in this direction. And this just tells me that the normal force is equal to mg cosine theta. Okay. Now if I do the same thing in the y direction, in the x direction, I look in the x direction. Well, there is only one force in the x direction here, and that's the component of the weight that's trying to pull it down the incline. And that's going to be equal to ma. And this now allows us to solve for the acceleration. The mass cancels. So the acceleration is just g, which is 9.8 meters per second squared, times the sine of my angle of incline, which is 15 degrees. So what is my acceleration equal to? What's 2.54 meters per second squared. And now I can use that with the kinematic equations to find the time. Let's say I want to find time. I don't know the final velocity, and I'm not trying to find it yet. So I look on my little chart. What doesn't involve the final velocity? It's the third kinematic equation, so we'll start there. Delta x equals v naught t plus 1/2 a t squared. The initial velocity, thankfully, was 0. If it wasn't 0, we'd have to use the quadratic formula to solve for time. But now I can just say that t is equal to 2 times delta x divided by the acceleration, and you take the square root. So I just took this equation and solved it for time. And now I can plug in my values. That's 2 times delta x was 5 meters, divided by my acceleration, 2.54 meters per second squared. And what is that equal to?
3.97.
So that's 10 divided by, is that right? Did you take the square root?
Oh, no. Sorry.
So it's 10 divided by 2 points, about 4, a little less than 4. So it should be a little less than 2. 1.98, yeah. 1.98 seconds. So that's the time it takes. Now, I could use the time, but what if I made a mistake? I don't want to carry that mistake forward. So what equation doesn't have time in it? It's the fourth kinematic equation, where v squared equals v naught squared plus 2a delta x. This is 0. So v is equal to the square root of 2a delta x, which is 2 times 2.54 meters per second squared times 5 meters. So that's something like 4 point something, or 5.04. I think that's right. So this will be, yeah, that's right. Meters per second. And we're done. So here's the whole problem. And the main thing is just to remember on an inclined plane problem to take the weight and break it up into the component of the weight that's perpendicular to the incline, which we call the y direction, the component of the weight that's parallel to the incline, which we call the x direction. And from that you can solve for the acceleration and then use the kinematics to solve for the unknowns. So remember that procedure, that procedure for using force, where you draw a sketch of the problem using given, find, and solve. You draw a free body diagram. You establish an x and y direction and break up any forces into their x and y components. You use Newton's second law equations in the x and y directions, and then you just use those to solve for your unknowns, that procedure that we studied a lot. That's the thing that I want you to know the most from this class and how to do. I mean, for those of you that might go on and study more physics or engineering or something like that, that's what's going to benefit you the most. So, you know, stay with it, learn it.